Hey guys, welcome back. So over the last few months on this channel, we've taken a look at various different iOS security related topics in this playlist here, the iOS Hacking and Security Research playlist. And many of these tutorials have consisted of various different exploit development tutorials for basic example programs. And all these exploits that we've been taking a look at have been very basic and beginner level and in places that you wouldn't really find in any sort of real world uses. So today in this video, to make things a little bit more interesting, we're going to be taking a look at one of the older jailbreaks, the Pangu iOS 9 jailbreak, the original one, the untethered one for 9.0 to 9.1 devices. I'm going to take a look at specifically how the exploit, the kernel exploit used in this jailbreak, works, and actually show you guys how you can replicate this exploit yourself and basically re-exploit it as if you were one of the developers behind Pangu. So this will be a great way to help you guys understand a little bit more about real-world exploits. And as well, this is a more interesting exploit than the ones we've covered. It's actually a use after free exploit in the kernel. So I'm going to explain what that is, show you guys how it works, and then basically walk through on how you can re-exploit it yourself to get some good practice with this kind of vulnerability. So the actual bug that Pangu exploited in this jailbreak is found within the IOHIDFamily kernel extension, and it's a use after free exploit, as I said, a use after free vulnerability. And to be able to actually walk through that exact vulnerability and on a physical iOS 9.1 device in this video, number one, it would take too long. Number two, people do not have those devices anymore. It's quite a rare version to be on. And number three, it also requires a lot of knowledge with IOKit programming and a lot of other things really unrelated to the exploit. So I'll do a lot of those other things in different videos, and then maybe eventually sometime in the future make a full sort of recreation of a jailbreak series or something like that. But for this video, as I already said, I've created a separate program that uses the exact same vulnerable code, so it's still the same vulnerability used by Pangu, but it's in more of a simplified environment to make it easier to understand and a bit more flexible for people to test it on, because you can run this on any device, whether it's higher than 9.1 or not. So go onto the Exploit Challenges GitHub on my GitHub page and scroll down, and you'll see that 3 hours ago we added heap level2.zip. So that's the name for this program. You can also see it down here. Heap level 2 is a use after free exploit. As I already said, it's the same one used in the Pangu jailbreak. So you want to go here and download the heap level 2.zip. Alright, so I've got the heap level 1 or heap level 2 app on the device, and I'm now SSH'd into the device from my Mac so you guys can see this a bit clearer on video. And what we're going to do now is just execute the program. So do /heap level 2. And this will just help us understand what it actually does. So you can see we get a little welcome banner, and then we have a little message saying about how it's based off of the Pangu, the UAF exploit by Pangu in 9.0.1 jailbreak. And then we get this little menu here. So we have 5 options. We have new device, terminate device, verify device, create data object, and then just quit. So this will exit the application. So let's quickly understand how this works. So if we type option number 1, you see we get this new device option. And a device in this sense is basically just a theoretical device. It doesn't really mean anything. It's just something that can store data, and it also stores a couple of pointers. So description is basically the data it will store. So you can put some A's or B's, just some characters that will allow you to not distinguish them between other characters when we look at them from a hex view. And you can see that we get a little message device created in green, and then we get returned back to the menu. So we can see we can actually terminate the device, which basically will just remove that device. Or we can verify it to check that it's all working well. So if we type option number 3, you can see device object seems to be set up correctly. Then we have this other thing here, option number 4, create data object. And this is not a device, it's just something that stores a simple string but from a file. So if we type 4, enter path to data, you would type the file path. So I've got a file called file.txt right there, and you can see data object created and populated with, and you can see the contents of that file. And finally we have the quit function. So it seems like a bit of a weird application, not very real world situated again, but because the code behind it is obviously real world, this should be good enough to understand how the jailbreak exploit this vulnerability. So the vulnerability actually lies within the terminate device option here. And the way it works, a use after free vulnerability, basically a generic use after free vulnerability, is when you attempt to use an object that was previously deallocated, basically. So with heap memory, let's quickly take a look at the heap layout and what happens when we create a new device. So when you select the new device option, we start, obviously, before anything happens, we start with an empty heap layout. So a heap is just a big chunk of memory. It will have addresses at the side so you can know where things are within the memory. And by default, all the memory will just be null bytes, basically. Everything will just be 0. There'll be nothing stored there. when you select option 1 and create a new device, and you populate, you give it a little description and stuff like that, it starts, the heap looks at for the latest free address, so by default it will be right at the top because nothing is populated, and it will basically store those characters. So you can see the 4 ones are the A's, the 4 2's are the B's, and I've also got some 4 3's, 4 4's for C and D. And after that we've got 2 addresses, and these are function pointers to 2 functions that are going to be used later on by this object. So that's basically the object created. That's the new device object. It's now stored on the heap. That's all it is. Now, because obviously that's now stored and it's in use, this little arrow pointing to the next free chunk will move down to the next free area underneath that, where the next set of zeros starts. And then if we go ahead and create something else, for example a data object, it would start there and you'd end up populating that area. But the problem occurs when we terminate the device. So what we can do is run the terminate, enter 2 to terminate the device, and what that will do is it basically frees this original memory that we've got the device stored in, but it doesn't get rid of it. It keeps the memory there, but it marks it as free. So basically the little arrow pointing to the next free chunk will move back up to the start. Even though there's data in there, it's not in use anymore, or it shouldn't be anyway. So then basically if we want to allocate something new, so we can create a new data object, we can then populate this with some new data or some new string that's found inside the file, and this will start writing it over the top of the data that was used for the previous device object. So you can see if we enter some lowercase a's, the 6 ones start filling up, and you can see we've entered enough to overwrite all of the data that we entered before, plus we've overwritten one of the addresses. So the address now contains 616161 instead of the ABCD, which it should have contained. So this is where the issue is. Because we didn't actually set the pointer of the device object to null, we can actually still refer to the device object. So after we've created this data object, what we could now try and do is actually use the method on the device object, and because it's obviously the stuff is still left behind there, we didn't actually null it all out, it still attempts to basically call that method because it thinks it's still existing. And obviously, since the original device data has been overwritten, when it attempts to call the method as part of the device object, it instead attempts to jump to the address 61616161, which is actually attacker control. So this is basically how you gain arbitrary code execution from this, because it attempts to jump to an address that you basically specify, because it shouldn't have been written there, or you should not still be able to refer to it. So this bug, as I said, is found in the IOHIDFamily kernel extension, which means it's part of the kernel. So when you actually exploit this, you gain arbitrary code execution at the kernel level, which allows you to obviously achieve a jailbreak. So let's take a look at how we can actually exploit this. We're going to be using GDB to debug this program and sort of examine the heap as it actually happens in a real situation rather than just on them diagrams. But first I'll quickly show you the source code just so you can better understand how this is vulnerable. So here's the heap level 2 source code. It's not available on the website, but you can see most of it from this video. So we're going to take a look through. You can see it's based off of the exploit once again. And at the top right here we have a device struct. So this is for the device object. So you can see we have a 32-byte data array of characters. And this is where you store the description, or that's what it's called, the description. This is just the data, so it's 32 bytes. Then we have 2 function pointers. One of them is to method, which is actually the method that verifies the function, the one that says the device seems to be running perfectly or whatever. And then we have the terminate one, which we'll talk about as well later on. So these both are function pointers, which is why it allows us basically overwrite these pointers when they're stored on the heap. So what we first do down here is inside of the main function we have the little menu system with the while loop, and then we have option number 1. We ask for the description, and then we pass that data to the new device function. And this new device function attempts to create a new device. So let's just find that new device here. You can see it will first malloc 256 bytes on the heap for the device, and then it copies in the data and it sets the function pointers and then says device was created. So that's obviously what we did there at the start, where we showed how the data was first written to the heap. But, however, when we terminate the device, if we choose option 2 for the terminate device, it will call this terminate device function. Now, this is the exact function found within the IOHIDFamily bug. This is the exact code copied one for one, and you can see what it basically does is it will terminate it, which doesn't actually do anything. This function just basically prints out that it was terminated. But what it also does is it calls OS safe release and it passes device. Now this is the unsafe function. This is what allows this to be used after free vulnerability. So if we take a look at this function, I've obviously simplified this down a lot for this example, but all it does is basically just free the device. What it should do to actually patch this, and the way that Apple did actually patch it, was they also set it equal to null. So as I said, we're going to examine the heap as the program was actually running, just to allow us to understand it a bit better. So we're going to first of all start GDB and open the heap level 2 application within it, wait for this to load up, and we're going to start by setting a few breakpoints, which basically means the program will stop at a certain area so that we can examine some things. So we're going to do disass main first of all. And actually, main is not really a very interesting function. All this does is to the menu. We want to put breakpoints in the more interesting functions. So first of all, we're going to disass the new device function, which is the function that's responsible for basically allocating on the heap the data for the new device. And you can see, let's just make this window a little bit bigger. Here is the disassembly for the new device function. And we want to basically put a breakpoint after the call to malloc, which basically will return into the register R1 the address of the new heap object. So here is the first call, and from looking at the source code I know this call is to malloc. So underneath this instruction we're going to copy this address here, and to make a breakpoint you want to type B star followed by the address, and you can see we've set a breakpoint now at this address. Now once that's called malloc, it's actually just allocated the empty space. You won't actually see anything new, so we also want to set a breakpoint once the data has been populated. So we just want to do it after the last call in this function, which is this one. So I'll do a breakpoint here as well. And we're also going to do a breakpoint in the terminate function so we can see what happens after it's been terminated. So we're going to disass terminate device. And we'll just do one right at the end here, just here somewhere, just so we can see the state of the heap after the device has been freed. And then finally we're going to do one when we create a new object. So create data object, and we'll just do one at the end of this, so after the data object has been populated. And there we go. So we're going to type run now to execute the program, and you can see it will load this up, and we just basically execute it as normal. But whenever we get to one of the points we set, it will stop and allow us to examine and look behind the scenes. So let's first of all create a new device, give it a description, let's put some characters we can recognize, AAA, BBB, CCC, enter, and we hit our first breakpoint in new device. So what we want to do now is examine the register. So you type IR for info registers and scroll up to see R0. So this register is the one that contains the return pointer from the malloc function. So this basically is the address at which the heap object starts. So we're going to copy that address and we're going to type X for examine and then do 64 words in hex space that address, and now enter that, and you can see we basically get the heap. This is what the heap currently looks like. On the sides of the addresses, similar to what I've shown in the diagram previously, and here are all the zeros as I showed also in the diagram. So there's nothing in the heap object at the moment. It starts from this address and currently it's unpopulated, as you can see. Now if we continue, you can see now we get a little device created prompt, and that means it's written all our data into it. So now if we just examine that same area of memory, you can see we now have the populated area. So it's the same address, and now instead of zeros we have some A's, some B's, some C's, and then we have the rest of the 32-byte buffer, which didn't actually end up filling up, so it just gives us some zeros in there. And after that we have the two function pointers. So we have an address here and an address here. These are both the function addresses for the method function and for the terminate function. So this is the way we're going to be able to manipulate these into achieving arbitrary code execution when we actually overwrite these after we've freed this object and after we've created the new data object. So let's continue again, and now we're going to just verify the device. So we'll just type free. You can see device object seems to be set up correctly. Now what actually happened there is it basically just called this function pointer. So it basically tested that the function pointer points to that function, and it displays this. So now we're going to terminate the device by typing 2, and you see we get another breakpoint here because we wanted to examine after the device is terminated. So that means it's been freed basically. So if we examine the same area of memory, what you'll see is that roughly the same data is there. Now it does mess with a few things at the start. This is to do with the heap chunk metadata, but we'll cover that in a different video. But you can see that some of the C's are still there, and then more importantly, the function pointers are still here. So you can still, the chunk layout basically is still the same, even though some of the data is gone. But it's not actually been completely wiped, and the pointer's not been set to null. So yeah, you can actually still refer to this even though it's been freed. So let's continue again. And now we're going to create our new data object. So for enter path to data. So we're going to do var mobile file.txt, which contains just a long patterned input. And you can see that it's now created that, and we get another breakpoint so we can examine. So what we want to do is examine this heap chunk again, the same area where the device object originally was. And now what we see is the new data. So 41, 41, 41, 42, etc. all the way through. And you can see this point here is where the first function pointer would have been. And this is where the second one would have been. And they've actually been overwritten now with these characters, because these are from this string here that was written into this heap area. So it's actually used the same heap area because obviously we freed the previous device. So now what we can do, continue once again, we can actually attempt to verify the device again, which, as I mentioned before, all it does is calls the pointer in this object. It basically jumps to the function this points to. So if we type 3 for verify device, you can see here we go, we get an error, kernel invalid address at 4949498C, and that is this exact address right here. So basically we've controlled the address it's attempting to jump to. Even though it's an invalid address, we could manipulate this and put this address to something that we know we want to jump to, for example shellcode or ROT payload, anything like that, and we now have arbitrary code execution. So this is basically how at a simplistic level, how a UAF vulnerability can be exploited. So now that we understand how this can be exploited, let's actually exploit it. So first of all, we need a place that we want to actually jump to. We need an address to put in here that actually points to valid instructions. Now inside of heap level 2, I've actually included a function known as winner, which for the purpose of this tutorial, basically what it does is call a shell, or it basically spawns a shell and gives you sort of a goal. So the idea is obviously to call this function. So all we need to do is basically put this address, the start of the function, into the spot right here, the spot where the first function pointer from the device object was, and that way when we attempt to reuse the device after it has been freed, with the new data that we actually populate it with the data object, it's attempting now to call the winner function, which will give us a shell. So to do that, we're going to quit GDB, and we're going to craft an exploit file, because as we know, the data object must come from a file, a text file. And to craft this with hex bytes, or to interpret hex bytes, we're going to use printf. So we're going to type printf, and now we need up to our offset padding, basically, for the amount of characters we need before this address. So you can see we've got 4141 all the way up to 4848, which is actually up to the h in this string. So what we need is printf all the way up to h, followed by the hex bytes in little endian, so reverse byte order for this address. So it's going to be 9C B80000, and you can enter them with printf by doing a \x, and then we're going to have 9C B80000, close speech marks, and then just basically pipe that into a new file. Let's just call this tutorial.txt. Enter that, and now if you ls and grep for tutorial, you can see we have tutorial.txt, and we can cat on that, and you can see here is the malicious string. So we have the junk characters and then the 2 question marks. Obviously we can't actually display these characters because they don't have valid ASCII characters assigned to them, but these 2 question marks substitute for these characters here, the address. So what should happen now is when we actually run heap level 2, and we pass it in, and we do all the stuff we said, and when we pass it in this tutorial.txt file, it should achieve us arbitrary code execution and spawn a shell. So let's try this out to see if it actually works. So I'm going to type heap level 2. Again, this is outside of GDB to prove that it does work. And we're going to start by creating our new device. Type 1. Description doesn't matter at all because it's going to be quickly overwritten, so just put some 1s in here. Device has been created. We can quickly verify it just for the sake of it. You can see the device object has been set up correctly. And then we're going to terminate the device. It's now been terminated, but again, as we already know, it's not actually been dereference, so we can actually still reference it right now and reuse it after it's been freed. And finally, we want to create our new data object, number 4, and we're going to give it the path to our maliciously crafted file. So var mobile tutorial.txt, which we know is going to write the specific bytes over the device object, so that when we try to reuse the device object, it's been modified in such a way that we call our own function. So there we go. You can see there, data object's been created. Now all we need to do is enter option number 3 and enter, and there we go, successfully pwned. Here is a shell, and you can see we get our little shell there, and this is a fully interactive shell, uname-a. You can see the device I'm running this on. It's coming from an iPhone 4. We can ls, we can go wherever, we can cd our whole way around the system, and we have a shell. So that is an example of how you can exploit a use after free vulnerability with a simple practice program. So obviously the real world version of this bug, the one that Pangu team actually exploited in their jailbreak, was a lot more complex to exploit because it requires very specific knowledge of the kernel zone memory layout, the kernel heap zones, and a lot of other things more specific to the iOS kernel. So use after frees are often quite specific to the specific platform you're running it on. But this is at its simplest form how you exploit these kind of vulnerabilities. So hopefully you guys learned something from this video. If you have any more questions about it, then you can leave a comment or tweet me at BLS1000 and I will try to get back to you. But that is pretty much it for this video. So again, check out the GitHub and actually try this out yourself, because it's a great learning experience. It actually teaches you quite a lot from messing around with these different applications. And by the time you're watching this video, there may even be new ones out, level 3, level 4, stuff like that. Also check out the ROP series, and I've also got videos for each of these levels. And also check out my new website, which I actually I've only mentioned in one video so far. Zygosec is actually a platform for learning about this kind of stuff. So there's not a lot on it right now. We've got the training section coming soon, and it's basically going to provide a lot of things like this and other resources and videos and written tutorials on how to get started with exploit development, reverse engineering, malware analysis, stuff like that. So go ahead and check out my website and the Twitter page for it, stuff like that, if you're interested. But that's pretty much it for this video. So I hope you guys enjoyed. Let me know what you think in the comments below. Let me know if you wanted me to cover any other jailbreaks or any other jailbreak exploits that were released in the past in a future video. And yeah, that's pretty much it. Thanks for watching. Don't forget to subscribe for more, and I will see you next time.